Hello, everyone. I am Dr. Steven Wong, and I'll be your moderator today for this webinar. I am a research and development engineer for the UC Institute of Transportation Studies, the California Resilient and Innovative Mobility Initiative, also known as CA-RIMI, and the UC Berkeley Transportation Sustainability Research Center. On behalf of the UCITS and CA-RIMI, we welcome you to this important webinar on changes in travel and air quality in California during COVID-19. We'll be hearing from two researchers, Professor Michael Kleeman from the University of California, Davis, and Professor Shams Tanvir from the California Polytechnic State University, San Luis Obispo, on their recent work on changes in travel and air quality during COVID-19 and the implications on the environment, public health, safety, and California's climate goals. Briefly about UCITS, the University of California Institute of Transportation Studies is an expansive network of faculty, research, and administrative staff and students dedicated to advancing the state-of-the-art in transportation engineering, planning, and policy to benefit the residents of California, the nation, and the world. Established by the California legislature in 1947, the UCITS has branches at UC Berkeley, UC Davis, UC Irvine, and UCLA. The UCITS statewide transportation research program is supported by the state of California through funding from the Road Repair and Accountability Act of 2017, also known as Senate Bill 1, and the Public Transportation Account. One of the unique and most recent initiatives funded by SB1 is CA-RIMI, an initiative of UCITS. The California Resilient and Innovative Mobility Initiative serves as a living laboratory, bringing together university experts, policymakers, public agencies, industry stakeholders, and community leaders to inform the transportation system's immediate COVID-19 response and recovery needs, while establishing long-term sustainable and resilient transportation in California and the United States. So just a few housekeeping items. If you run into technical issues, let us know by typing a message in the chat box. If you have questions for the speakers, then click on the Q&A icon at the bottom. A screen will pop up where you can enter your question. Speakers will type responses to questions throughout the webinar, and some questions will be responded to live after presentations when we have the time. With that, I first want to introduce Professor Michael Kleeman. Professor Kleeman has been a faculty member in the Department of Civil and Environmental Engineering at UC Davis for 22 years and has degrees in mechanical engineering from the University of Waterloo and in environmental engineering science from the California Institute of Technology. Professor Kleeman's research is focused on urban and regional air quality problems using a wide variety of measurement and modeling approaches. His recent areas of interest include the adoption of new energy sources and the resulting impacts on air quality. Welcome, Professor Kleeman.
Thank you, Stephen. And give me a moment while I get everything going here. All right, I'm very happy to be with you all today and talk about our work during the COVID-19 period, looking at ozone formation in California. And we're going to focus on some direct measurements of that ozone formation and what it means both during the COVID-19 period, but also more broadly for California's ozone control program. So ozone is a gas phase oxidant in the atmosphere, and it causes health effects that are related to inflammation of the lung tissue and making asthma worse. It definitely is something that we've been trying to control for many years. Now, more than 40 years ago, scientists in California realized that there were two precursors to ozone formation, and I'll refer to those throughout my presentation today: oxides of nitrogen, or NOx for short, and volatile organic compounds, or VOC for short. And we realized that there is a balance between these two things, and we have to recognize that balance as we design our emissions control program. If we're in a certain regime where one precursor is more effective at controlling ozone, then we should focus on that precursor and not the other. And so that insight has allowed for more than 4 decades of progress reducing ozone concentrations. If we look at the concentrations in the South Coast Air Basin, we've made great progress reducing concentrations over those decades. But more recently, we've stalled out a bit. We haven't made as much progress and maybe even seen some backsliding where concentrations have gone up, still above the health-based standard that we'd like to see. And so the question becomes, why is that happening? And the model calculations that we rely on inherently have some uncertainty, and we really need some measurements to try to provide more of a weight of science for that. And that's where our project came in. We wanted to directly measure that ozone formation and how effective controlling NOx or VOC would be at lowering those ozone concentrations. So I'm going to present this as sort of the conclusions first, and then I'll go through my methods to try to explain how we got there. So satellite and ground-based measurements combined show that the ozone responds to NOx and VOC differently across different seasons in California. The limiting precursor is VOC in the spring and the fall, but the limiting precursor is NOx in the summertime. Present day ozone concentrations, the peak concentrations that happen in the summertime, would be best controlled by a NOx emissions control strategy. But that's going to lead to some increasing ozone concentrations in the sort of transition seasons in the spring and the fall. And furthermore, it will lead to some increasing concentrations in the urban cores of cities, which tend to stay VOC limited throughout the entire cycle. And so really what we're seeing here is that there's going to be some winners and some losers in the ozone control program. And it's important to understand where they're going to happen and who that's going to be, perhaps, to think about how to mitigate that, whether any extra steps need to be taken moving forward. So let's talk about how we come to those conclusions then. We implemented 1 year of monitoring for ozone concentrations in Sacramento, California at a ground-based site. This happened during April 2020 through April 2021. I'll focus on the measurements in 2020. And I'll just note, of course, that this was the COVID-19 period where we had rapidly changing transportation patterns as well, especially in April, the early part of this measurement period. And I'm going to try to put that in context as we go forward. Now, what we did at the ground-based site was to use what we call smog chambers. And these are Teflon reaction chambers where we draw some ambient atmosphere into them, and we can control what happens in those reaction chambers so that it's repeatable across the entire season. We don't have to worry about how brightly the sun was shining because we're going to use the same UV lights to drive the reactions in every day of the year. Now, in one chamber, that serves as our baseline measurement for ozone formation. The second chamber will add a little bit of NOx, one of the precursors. And in the third chamber, we'll add a little bit of VOC, the other precursor. And by comparing the three chambers, we can look at the sensitivity of the ozone formation to our different precursors and understand which precursor would be most effective to control in order to reduce those ambient ozone concentrations. Now, we first have to recognize, though, that the ambient atmosphere is changing throughout this time period. As the seasons change, we get different changes in the precursor concentrations in the baseline bag. And so what we see most strongly, I'll focus on the lower plot here. I've got month of the year on the lower axis, and I've got the concentration of the VOCs on the vertical axis, both measured in our ground-based chambers and then also observed from above with satellites. So the satellites use the right axis here, and they're the diamonds, and the chambers use the box and whisker plots, and they're the left axis. And what we see is that as we move into the summer, we get higher concentrations of that precursor VOC, and that's probably because of the plants. The biogenics around us emit more in the summer, and so we see higher concentrations in the summer just naturally. Now, in the NOx, the oxides of nitrogen, it's kind of the opposite story, where the highest concentrations tend to occur in the winter transitioning into spring, and then back in the fall transitioning back into winter. And that's because the mixing in the atmosphere maybe isn't quite as vigorous in some of those time periods. And then also we're using more fuel for heating in those time periods. And so we see higher concentrations of the oxides of nitrogen of the NOx. Now, when we switch and look at our studies to examine the precursors and how they affect ozone formation, then we see a seasonal pattern as well. And I'm going to start by focusing on the upper panel. Again, I've got month of the year on the lower axis, and I've got box and whisker plots for the chamber measurements on the left side, and I've got the satellite observations on the right side. And what I'm showing is how much ozone increase do we get when we add some oxides of nitrogen to the experiment. And what you can see is that in the summer, we get positive ozone formation when we add oxides of nitrogen. But this dashed line here is the 0 line. And anytime you see a reading below that, it means that you're actually destroying ozone. You're taking it away when you add the oxides of nitrogen. And this matches what we understood from the chemistry 40 years ago, but it's just putting it into context of where are we in present day on this sort of chemical regime for ozone formation. So why does this cycle happen? Well, it happens because those biogenic VOCs in the atmosphere provide enough of the precursor VOC in the baseline measurement. So when we add NOx, we're actually getting more ozone. So we call that a NOx limited situation. And controlling NOx is the right way to go when you have this situation. In the spring, winter, fall time periods, though, we're not in that situation. We're actually, we don't have enough VOC. And when we add NOx, we actually suppress ozone formation in those seasons. Now, what does this mean for maximum ozone concentrations? And so what I'm showing now is a plot where on the lower axis, I've got the baseline concentration of ozone. And on the vertical axis, then I'm showing the change in ozone as we add a little bit of that precursor NOx in the upper panel or the precursor VOC in the lower panel. And what we see is that for all the higher concentrations to the right of these plots, they are NOx limited. And so controlling NOx would help reduce our maximum ozone concentrations that we experience. But remember that the health-based standard that's encoded in the National Ambient Air Quality Standards is 70 parts per billion. And so any of these boxes to the right of where my cursor is at the 70 part per billion line is of health concern. And some of those concentrations are actually in the VOC limited regime, not the NOx limited regime, where actually if we would take away some NOx, we expect that these ozone concentrations would increase, not decrease. And so this leads to the conclusion then that there's not a one size fits all strategy that will lower all of the ozone concentrations everywhere in California that are of a health concern. If we use NOx to control the ozone, then we're going to lower the peak concentrations, but we're going to increase these intermediate concentrations that are still above the health-based standard. Now, there is a weekday effect that's well known, where there's fewer trucks on the highway on the weekends. And so that lowers the NOx concentrations on the weekends. And we can see a difference in ozone concentrations as a result of that. It's a well-known weekday effect. But that effect has been getting milder as we go forward in time because emissions have been controlled from the trucks and from the cars. And so we're seeing less of sort of an ozone enhancement is what we would see on the weekends. So we can still see some evidence of that here. I'm showing month of the year again. I've got my box and whisker plots. The shaded bars now are the weekdays. The weekends are the open bars for each of the months. And you can see that the open bars tend to be a little bit higher than the shaded bars, but not as much as they would have been 20 years ago. And only some of these differences are statistically significant. Now, that's a sort of a foreshadowing for what was the effect of COVID-19. In COVID-19, we had a great reduction in the light-duty vehicle traffic in April, not as much in the heavy-duty traffic. And I'm comparing now in 2020 versus 2021 in April. Did we see a change in that sort of chemical regime for ozone formation? Did it change our strategy for what we would reduce? Would it be NOx or VOC? And really the answer turns out to be it didn't make very much of a change at all. And that's, because perhaps the mobile sources, the light duty vehicles aren't providing a big enough perturbation to really jump us into a whole different chemical regime. It also depends on where we are in the annual cycle, in the seasonal cycle of things. But April was a transition month. And so we would have expected to see a sort of a big difference perhaps in that transition month. But we didn't see it, I think, because again, the light duty vehicles are just not dominating enough of the NOx that's in the ambient atmosphere to move us to a whole different chemical regime. Any NOx control strategies that we adopt are going to have to go beyond the light duty vehicles to look at all the different combustion sources to get enough NOx control to really make a difference. So that's an insight that comes from the COVID-19 comparison, put it in context with this whole year of measurements. Now, we use the satellite information to help us understand whether this is just a phenomena that's local to Sacramento or whether this is statewide. And so this is a really complicated figure, and I'm not going to try to explain all of it, but I want to just look at the different plots of California and look at the colors. Each plot corresponds to a different month that we've got listed here, and the colors correspond to the most efficient control strategy. When you see green, we would want to control VOCs to reduce ozone. And when you see red, we would want to control NOx to reduce ozone. And what you see is that as we move from spring into summer, more of the state goes red. And that matches what we saw in Sacramento. And so we think that this is an observation that's applicable to most of the state, this seasonal pattern sort of transitioning into NOx control being the most effective strategy in the middle of summer. But notice, however, that places like Los Angeles, where I've got my cursor here in September, stay green for the whole year. And so the urban cores really don't make as much of a transition as the rest of the state does. And so we may have always a persistent VOC limited problem in the urban cores until we get a lot of NOx control, and then we expect to see benefits. Also note that wildfires, which are sort of the outlines here, we had a lot of those during our COVID period. It was a tough year. They generate a lot of VOCs. And so you can see, especially in October, that the areas around the wildfires are best going to be able to control ozone by reducing NOx because there's an abundance of the VOCs coming off the wildfires. And so that's something important to realize as well. So what does this translate into for different air basins? Well, they all go through that seasonal transition where we are going from a sort of a VOC limited regime to a NOx limited regime in the summer, and then back to a VOC limited regime in the fall. That's sort of a universal observation for the whole state. And what it really just means is that we're going to need not a little bit of NOx control, but like what we observed in COVID-19, but a lot of NOx control if we want to be able to reduce ozone concentrations for the entire year. So my conclusions now, restating them for the second time, the ambient VOCs follow a cycle where they're higher in the summer because of the emissions from plants. And the ozone formation mirrors that cycle. Essentially, there's too little VOC in the winter, in the early spring, and the fall. And so VOC limits are the limiting precursor to ozone formation. But in the summer, because we got all those VOCs from the plants, really the limiting precursor is NOx. That's your most effective control strategy. So we can reduce our peak concentrations present day by going after NOx. But that's going to increase the ozone concentrations in some of these urban cores that already have a lot of NOx there. They've got too much NOx almost already for efficient ozone formation. So reducing some of that NOx is going to lead to increasing ozone in the urban cores. Long-term deep NOx reductions should eventually solve that problem where NOx will again become the limiting precursor, but the magnitude of that will have to be higher than what we saw during the COVID-19 period in order to be effective. So the policy implications then is that there's not one strategy that's going to fit everybody near term. As we reduce NOx, we're going to reduce the peak concentrations that we currently have at our monitoring sites around California. But that just means that the highest concentrations will shift inwards towards the urban cores, and it'll be those places that get the highest ozone concentrations until we achieve much deeper NOx concentrations. So I think as a policy implication, it's important to map that out and understand where are we going to see those ozone increases? Who are the populations living there? And it may well be the case that some disadvantaged communities are going to be adversely impacted by that. We want to understand that and think about whether there's any offsetting factors. There may be some human-made VOCs that we can reduce, volatile chemical products and other things. Maybe we can try to get some amount of ozone control with those as well that may benefit those populations. And then finally, wildfires are a major source of the VOCs that produce ozone. They're hard to control, they're unpredictable, and NOx emissions controls would be an effective strategy when we're impacted by wildfires. So I'll just conclude by thanking the sponsors for supporting this work. This work was supported both by the California Air Resources Board and the Coordinating Research Council, in addition to a grant from the University of California Institute of Transportation Studies. And then I should acknowledge the South Coast Air Quality Management District in Los Angeles for funding a pre-study that sort of set the stage for the research that I shared today. So with that, I will be happy to try to answer any questions during the chat window or live when we get to that part of the seminar today.
Thank you so much, Professor Kliman. We will now move into our second presentation from Professor Shams Tanvir, who is an assistant professor in civil engineering at Cal Poly San Luis Obispo. He researches transportation technologies that minimize energy consumption and emissions while enhancing mobility, efficiency, and equity. Dr. Tanvir received his Ph.D. from North Carolina State University and was recently a research faculty member at the Center for Environmental Research and Technology at the University of California, Riverside. Currently, he is serving on 2 Transportation Research Board committees, the Highway Capacity and Quality of Services Committee and the Transportation Air Quality and Greenhouse Gas Mitigation Committee. Welcome, Professor Tanvir.
Thanks, Stephen, for the warm welcome. Good afternoon, everyone. So I'm Shams Tanvir, and I am a professor of civil engineering in Cal Poly San Luis Obispo. And today I'm going to talk about a project that I have been working on for the past year. And this work is in collaboration with my UC Riverside colleagues, Professor Matt Burke, Professor Sunny Ivy, and Dr. Kanak Bariban Simpson. So before we begin the presentation, the motivation for this work came from the level of traffic reduction that we saw because of the COVID-19 pandemic. So in the top plot that you can see, in the different weeks following the COVID-19 pandemic, the regional vehicle miles traveled in the South Coast Air Basin area, that dropped significantly, as much as 35% in early April, but it slowly recovered. But in the bottom plot, as you can see, this one is showing the VMT reduction and recovery in the different counties within the South Coast Air Basin. The bottom 3 curves are corresponding to Orange County, Ventura County, and Los Angeles County. So those counties saw greater reduction in average vehicle miles traveled. However, the other counties in that region, like the Riverside County, San Bernardino County, did not have that level of traffic reduction. Then we also saw the trends over time, that we saw a V-shaped curve in the reduction of traffic activities. There was reduction and there was recovery, but that trends was not similar in all the different places. So our motivation was to study locally how that trend was changing in terms of people's change in travel behavior. And what we also understood as of now, the plot goes up to April 2021 on the top, and you can see still there is about 5% of traffic drop, even in the peak hours. So the traffic level have not really recovered fully. I want to begin with what we have learned from this project so far. So the first thing that we have learned is that the traffic shifts are locally variable, and the declines in traffic flow were observed in the entire South Coast Air Basin. However, the big pictures doesn't tell the full story. It is not until you start zooming, we don't see that the traffic level recovered at different times and scale across the different subregions within the South Coast Air Basin. And also the level of traffic drop, it depends on who lives on those communities and specifically the people who are traveling in those areas. So the more disadvantaged communities, that saw lesser level of traffic drop. And what we also found, the traffic flow level rebounded in disadvantaged communities faster than the other communities. And we also investigated air quality in the South Coast Air Basin area. So on the right, you can see the concentration of carbon monoxides in ppm in one of the monitors near Anaheim. And the top blue line shows the concentration or the diurnal profile concentration for CO before the COVID starts. So that's from January to March of 2019. The red line is right after the lockdown was imposed. So between March to May, that's when the carbon monoxide level reduced in most of those areas by up to 50%. And then the yellow line is showing the second stage. This is May to June of last year. You can see the yellow line is recovering a little bit over the red line, but still not had gone back up to the blue line. So we saw that near road pollution actually reflect the traffic trends, and we also saw similar trends in the non-near road locations too. So this plot here on the right, it's showing the Caltrans District 7 VMT drop for total vehicles using the color blue, and the orange line is showing the truck VMT drop. And you can see both of these type of vehicles have this V shape that we talked about earlier. So during the first week of March, that's when traffic level started to drop. And in the first week of April, that's when we saw up to 35% of VMT drop. And this is for the afternoon peak period. And slowly in the months of May and June, we saw recovery. And around June, the last week of June, we saw about the traffic levels were just up around 5 to 10% down from the pre-COVID level. On the left, we have mapped the traffic sensor information derived from the Caltrans PEMS monitors, and then we map them into the census tracks on those areas. So the different colors represents how the traffic levels were changed compared to the pre-COVID level. So the light yellow and orange, those are showing higher than pre-COVID level traffic. And you can see this plot is from March, the last week of March. There is not many areas that showed higher than pre-COVID level traffic. And then the pink is showing slight decrease. The purple is greater than 25% decrease compared to the pre-COVID level. And the dark blue is when we have significant amount of decrease, as much as 50% or more decrease compared to the pre-COVID level. So you can see the most census tracts mapped here saw a drop of about 25 to 100% in the third week of March. And then we'll see later on in the next video that how that pattern changed as we move along during the COVID timeline. So this video starts from the first week of January. You can see most of the areas are keeping steady, maybe just above the baseline level. But right around the second and third week of March, we see a lot of pink and purple appearing in the screen. And what's interesting during the height of this pandemic that you can see there is these different areas of blue, and which I mentioned earlier, that blue means greater than 50% reduction of traffic. And if we look at those regions where they are located, you can see most of them are located near the coastal regions in Orange County, Ventura County, and some of the well-off neighborhood in the Los Angeles County. Whereas the purple and the pink points or locations were mostly in San Bernardino and Riverside counties and some of the eastern Los Angeles counties. And moving along in the recovery periods during late April, early May, and in June, you can see some of the areas were picking up traffic fairly quickly. Those areas are mostly in San Bernardino and Riverside counties and southeastern Los Angeles counties. So there was a significant amount of heterogeneity in terms of which areas saw the traffic level reduction and how those traffic levels were recovering from the pre-pandemic levels. So in this slide, what we try to do is we try to convert the information that we saw in the map and try to correlate them with some sort of socioeconomic variables. So in this case, the plot on the right is showing on the x-axis is the Cal Enviro Screen 3 score, which is a composite score of what's the socioeconomic status of the people living in different census tract and what's the pollution burden for those people. So the lower is the score, it's actually the less disadvantaged areas, and the higher is the score, that score shows the more vulnerable population in terms of socioeconomic and environmental exposure. So what this plot is showing is it's showing the relationship of the percentage of change in traffic. So the negative numbers showing the traffic drop with this Cal Enviro Screen score. And the blue line here is the logarithmic fit of the different census tracts in the Southern California area. So on the left, you can see in the well-off areas, we saw as much as 50% average traffic drop, whereas on average in the least well-off areas or more environmental the disadvantaged areas, we saw about 20% drop. So there was significant difference between the different areas depending on where or which people or what type of people live in these areas. And so the fit line actually shows the rate at which the disproportionate impact of decrease of traffic level is happening throughout the Southern California area. So in the next slide, what we try to show is how that disproportionate impact is varying along with time and across the different events throughout the pandemic. So the left one is showing the intercept of that relationship. And as we move along from January through September in this plot in the x-axis, we can see in the different weeks, right after March 1st, that's when traffic drop level started to happen. And the height of the drop was happening in the week of March 22. So the intercept is representing the traffic drop level for the least disadvantaged communities. And we saw in those areas, we saw as much as 80% reduction in some cases. However, the slope of the relationship represents the rate at which these disproportionate impact were happening in some of the communities of concern. So for example, we saw the values for this slope was highest during the first level of the lockdown. That's when the first lockdown was happening. And then around the first and second week of May, that's when we had around the second week of lockdown. And we saw a significant amount of rise of these slope terms when there was some protest happening near the Los Angeles area due to the George Floyd death and some other reasons. So we saw these values were spiking because of the different events that was happening around the area. And the more acute was the impact of that event, the sharper was the contrast. Next, we try to see how these air quality impacts are localized and how those air quality impacts are due to the change in traffic level that we saw from the traffic monitoring sensor. So here we have this plot on the right that's showing the relationship between traffic level drop and carbon monoxide concentration change near a neighborhood location near I-5 in Anaheim. And then we saw that the trend of decrease in carbon monoxide concentration along with decrease in traffic level, it actually were present in this location as we saw in all the other monitors in our study area. But that level of decrease shown by the red line here is not uniform. And so the changes are highly localized based on the local meteorology and local land use patterns. So in this case, this was a location near a school and residential area. So the highway level of traffic drop might not be directly relevant for the level of traffic related air quality change that we can see in that location. What we also saw is that the level of truck-related pollutant like the NOx level was significantly higher compared to what we'll see otherwise during this time of the year. And then we saw the NOx level for this particular sensor near I-10 in Ontario, 81 Avenue, that the NOx level was dropping down near March 30, but then it recovered very quickly at around April. And the plot on the bottom right is showing how that NOx concentration level changed with the level of traffic drop. So here it's interesting fact is the 0% line is shown by this green line here. And you can see most of the changes in NOx concentration was on the positive side, which means net increase from the baseline level. And you can see some of these activities that can happen in those areas because of the presence of warehouse and because of increased activity of trucking in those locations that can contribute to higher level of NOx, even if the traffic levels were always dropping in these cases. So there was between 35 to 10% drop of the overall traffic level in those locations. So all in all, the potential policy implication for this work is that not every areas had access to telecommuting. The well-off areas had basically had jobs that are more suited to do telecommuting, whereas the communities that have concerns regarding environmental justice did not have adequate access to remote work because of their nature of their work and what kind of technology they can use for their jobs. So one idea is that we can target incentives for future telecommuting related policy initiatives that can target those communities of that are communities of concern that has concern with regarding environmental justice. And also because of the pandemic, we saw a increased consumption of online shopping items, and that led to more warehousing activity. And what we saw near the I-10 in Ontario and Itiron Avenue, we saw increased level of warehousing activities in those locations. So we need to craft policies that can help us manage additional trucking activities specifically in the inland regions in the Southern California air basin. So with that, I want to thank my collaborators, Dorak, Sunny, Kanok, Matt, and this work was funded by Institute for Transportation Studies through the SB1 fund. And thank you so much. I would take your question if you have any through the chat and also from the next live session. Thank you so much.
Wonderful. Thank you so much, Professor Tanvir. We will now move into a great opportunity to hear from two guest respondents on their reactions to the presentations, including how the research could be applied to California policy. First, I want to introduce Scott Epstein, who leads the Air Quality Assessment Group at the South Coast Air Quality Management District. His group specializes in the analysis, interpretation, and dissemination of air quality and meteorological data. Scott has a Ph.D. in chemical engineering from the Center for Atmospheric Particle Studies at Carnegie Mellon University. Welcome, Scott.
Thanks for the introduction. First, I want to just talk a little bit about my agency that I work for to provide some context for my comments. So the South Coast Air Quality Management District is the local regulatory air quality agency for the South Coast Air Basin and the Coachella Valley. And that region covers portions of LA, Orange, San Bernardino, and Riverside County, and we have about 17 million people within our jurisdiction. So as you may know, we've made huge strides improving air quality, which Professor Kleeman showed on his ozone trend plot. But unfortunately, we still have the worst ozone pollution in the country, and we don't attain federal ozone standards. We also have some challenges related to fine particulate matter. We're on the cusp of attaining the 24-hour federal standard, and we're working hard to attain the annual federal standard. So first, I wanted to just talk a little bit about Professor Kleeman's presentation. So this presentation provides really useful results from a regulatory perspective, and I saw this for the first time the other day and really excited at the results. So basically, we know we need to reduce ozone significantly to meet our clean air goals, and we want to get there as quickly and as cost effectively as possible. Our existing air quality control strategy is based largely on chemical transport modeling, which shows very similar results to this study. With chemical transport modeling, we can project the future state of the atmosphere many years into the future. So our attainment deadlines, 2023, 2031, and then there's another one in the mid 2030s. So we need to project what emissions will look like far into the future, because we reach a different chemical regimes as emissions go down over time, as Professor Kleeman alluded to. So with our modeling, we also find that reductions in NOx without some VOC reductions will lead to short-term increases in ozone in the most urbanized portions of the South Coast air basin. So our strategy aims to avoid that ozone increase. And the way we do that is we need very large reductions in NOx. So about an 80% reduction from 2020 levels by 2031. And we also need some targeted VOC reductions to help avoid those short-term increases in ozone. So we have a NOx-heavy strategy. However, we do have some of the sort of, you'd say, easier VOC reductions in targeted areas to help avoid that ozone increase. And we, along with Professor Kleeman, find that if we remove all of our anthropogenic VOCs, that's not enough to bring us into attainment. So we really the only way to attain the federal standards is to make significant reductions in NOx. So these measurements, like I said, are really consistent with our control strategy, and they help build confidence in the model, which is really nice for us. And also the satellite analysis, I thought was great that it makes these measurements that were done, just in the Sacramento area more broadly applicable to the rest of California. And I'm really excited to read the paper. So now I'll talk a little bit about Professor Tanvir's presentation and kind of the regulatory significance of that. So this was really interesting for me to see because in my group, we spent a lot of time looking at changes in air quality during the first few months of the pandemic last year. And the subject's really relevant, not from just the perspective of this one particular time period, but we're trying to use it to serve as a real world experiment for what would happen if we drastically reduced emissions, as we aim to do over time. And as Professor Tanvir alluded to, the truck traffic didn't decrease nearly as much as passenger vehicles. And what happened was when the ozone season started to ramp up in late April of 2020, when we had this really intense heat wave, the NOx emissions weren't really too far below normal, mainly because trucks are the dominant source of on-road NOx, not cars. And this was contrary to many people's perceptions and a lot of the media's perceptions because of how empty the roads looked in the absence of passenger vehicles. So everybody, they drive around, they'd see, oh, there's no cars on the road, air quality must be much better. But in reality, trucks weren't affected that much. Trucks are the dominant source of NOx. So, we didn't really remove enough NOx, as Professor Kleeman alluded to really move into a different chemical regime. And get some major reductions in ozone. Also, we have some indications that the levels of VOCs were fairly typical throughout 2020, potentially due to increased use of cleaning and disinfecting, which kind of replaced the reductions that we saw from a decrease in other activities like mobile source activities. And we still saw plenty of high ozone episodes throughout the summer. And actually overall had a pretty bad season from a historical perspective. We reached some values that we hadn't seen since the mid-90s. So the bottom line, kind of the take home from COVID and how it can be applied to, as a real world experiment is that it was really interesting, but it's not exactly the same proportions of NOx and VOC emission reductions that we expect to get with our ozone control strategy. And as you've seen from Professor Kleeman's presentation, NOx is important, VOCs are important, and also the ratio of NOx to VOC emissions are all important, which this real world experiment didn't simulate exactly. So Professor Tanvir also makes some astute policy recommendations arising from his analysis. One recommendation is for policies that facilitate telecommuting. So we have a rule on the books, Rule 2202, which was adopted in 95 and amended several times, which aims to reduce on-road vehicle emissions from commuting. And this rule requires that large workplaces reduce their commuter emissions through a menu of options. So one of the options is that employers get credit when their employees telecommute. So that is already part of our existing rule. However, it's very possible that we will amend Rule 2202 again once COVID sort of settles down, and it's still up in the air. I don't think we know exactly which direction it'll go, but it's very likely that telecommuting will play even a larger role in this rule amendment. Another recommendation stemming from Dr. Tanvir's work is related to reducing emissions from warehouses, and I have some very current news about that. So we also recognize that heavy-duty trucks are a major source of NOx and air toxics, especially in communities with a large warehouse or logistical industry presence. And in fact, NOx emission sources that are associated with warehouses produce roughly the same amount of NOx as all the refineries, power plants, and other stationary sources in the South Coast Air Basin combined. So we have this new rule called our Warehouse Indirect Source Rule, which is 2305. This was approved by our board on Friday, and it requires warehouses larger than 100,000 square feet to directly reduce their NOx and diesel particulate matter emissions, or to help facilitate emissions and exposure reductions in nearby communities. So we are working on these policy issues. So thanks so much for the opportunity to comment on these interesting presentations.
Thank you so much, Dr. Epstein. We'll now hear from our second respondent, Dr. Toshi Kuyama, who is the supervisor of the Atmospheric Processes research section of the Research Division at the California Air Resources Board. He coordinates atmospheric research needed to efficiently achieve the ambient air quality standards and California's climate change mitigation goals developed from AB 32, SB 32, and SB 1383. He received his PhD and MS in Civil and Environmental Engineering from UC Davis while studying the effect of mobile source emission reduction measures on ambient air quality. Welcome, Toshi.
Thanks, Steven. And first of all, I wanted to thank both Mike and Shams for a very comprehensive presentation. It really did cover a lot of the questions that we had regarding air quality during the COVID period. Scott actually covered a lot of the details, so I'll speak more generally to this for both presentations. I really thought that both presentations highlighted the complexity of our air quality management challenges related to emission sources and chemistry that are really different from region to region and also season. I thought that Mike in particular did a great job reiterating the need to really understand the fundamental directionality, right, of the atmospheric sensitivity of ozone formation to optimize our existing air pollution reduction pathways as we cross these ozone ridge lines. And although this past year was very unfortunate period, it did force us to experience what it means for emissions from transportation activities to be reduced significantly. So experiments like this and studies like this really helped us hone in on what it takes for California to achieve the national ambient air quality standards in the future as we move towards electrification of on-road fleet and carbon neutrality. I also did want to note that Mike's take-home message on ozone, and Scott mentioned this as well, for ozone reduction in particular, is very consistent with CARB's emphasis on additional NOx reduction needs for long-term gains. But one of the most interesting points that he made is that not every region will experience the same level of gains, at least not at the same time. So, as we get deeper into this issue, we need to be cognizant about how we address these spatial temporal differences effectively and with consideration for equity as we reduce directly emitted air pollutants, but also pollutants like ozone that are secondary in nature. And so exploring short-term ozone mitigation through VOC reduction, for instance, really shouldn't be discounted, regardless of the major NOx reduction push that we have. And we really need to think about how we can continue to curb ambient ozone trends effectively throughout the year, and not just in the context of the ozone design values, but ambient ozone levels, particularly over disadvantaged communities and local scale air quality. So with that, thank you for having me here, and I'll be happy to answer questions during the live session.
Olga, thank you so much. I really appreciate it. I think we can now transition into a Q&A period. So we'll have the panelists and the respondents as well as the speakers go ahead and put your cameras back on. And I think something that has really come up throughout all these presentations that is mentioned in one of the Q&A questions is about the fact that there is differences geographically, and even as far down into a neighborhood block or even street level. But there's also, of course, broader impacts across a whole region as well. So there's kind of that difficult balance. And so the question that really came up was, should we be specifically investing in our emissions control strategies in targeted areas? And also what criteria could be used for identifying those targeted areas? Scott, you mentioned very briefly about warehouses, but I think going to open this up to everyone, because I think this is something that everyone touched on, is the locality of some of these impacts as well as sources. So it's kind of both ways. Who would like to start? Go ahead. I think Michael might want to start.
Well, I just wanted to make the comment that certainly the different pollutants have different spatial patterns. Some of them, are very sharp because they're directly emitted, and it's that direct emissions builds up sharp spatial gradients. But some of them are much more broad. And so we had examples of both in the presentation today. The carbon monoxide, a directly emitted pollutant, you're going to see very sharp spatial gradients for that. But ozone, being a secondary pollutant, it tends to be much broader. And so it really depends on what pollutant you're looking at. The ozone, as an example, perhaps you can get some quenching of ozone where you emit NOx and you have it react with the ozone, and it produces sort of an ozone hole right around, say, a transportation corridor like a freeway. But then we didn't talk about NO2, which is one of the reactions, one of the products of that reaction. And so, if you look at these things, you quickly get into the chemistry questions and the timescales for all these things happening. So there's no simple answer to that question. I think it really depends on which pollutant you're focusing on, and which are the major sources around it, what the timescales and spatial scales are going to be. So that's not an answer other than it's complicated.
And I can just add here, so we are actually addressing disadvantaged communities throughout the state with AB Assembly Bill 617. So basically, air quality was traditionally regulated just based on the worst air quality in your air basin. And we still regulate that way, but AB 617 kind of changed the paradigm where you focus in on communities that are particularly vulnerable to air pollution due to socioeconomic conditions, and then also particularly burdened by air pollution. It's not as targeted to ozone, it's more for air toxics or diesel particulate matter. And we have 6 of these communities in our air basin, and there's communities throughout the state. And there's a really intensive program that's done along with guidance from the community to help provide, targeted incentive funding, regulations, more targeted inspections, a monitoring campaign to really address these disadvantaged areas sort of from the ground up.
Stephen, I would like to add to what Scott had mentioned. I think one of the most critical thing that us as an agency and also researchers need to do is communicate better, reach out to communities, and really understand the issues at the ground before making judgment calls. And we do have very comprehensive tools like CalEnviroscreen, for instance, that we rely on to really understand the spatial disparities of disadvantaged communities and what we see in California as a major environmental issue. But as we gain additional tools and capabilities like satellite measurements, for instance, that Mike mentioned, and what Shams has mentioned with a more detailed activities data, we have a better chance at really identifying the specific problems and being able to work with the communities to address that. So I do encourage everyone here to really reach out to people at the community level and the district and larger agencies to work together more closely, because that's really the only way to accelerate this process.
Yeah, and Stephen, I would also like to add to Toshi's comment here is we tend to kind of generalize how people travel in a particular area, generalizing their activity patterns. In reality, specifically these people who are living in these disadvantaged communities, most of the time we'll see these people live in pockets. So there are wealthy neighborhoods around, and then there are certain people who don't have access to active transportation mode, access to transits, and some other effective transportation options, including these emerging fuel options like electrification and others. So how do we take into account of those lack of access and into that spatial level of granularity? And also, how do you forecast in future? Because what Scott mentioned is like, he's using the information about people's travel and travel activities as an input to those this future emissions or pollution prediction models. Then how, if the upstream data are not really updated, doesn't have high fidelity in them, then we don't really get to know about what's happening in the next steps. And that kind of brings very well with what Michael had presented, because even if the activities are changed, but the downstream level chemistry and the pollution and the air quality changes are so complicated. So we ought to be able to do a better job of understanding and improving the data richness in all the different steps in order to get like a very targeted pollution reduction program.
Yeah, that's a fantastic point about getting the right data to inform the models, and especially as we look from a projection standpoint. We got a question related to there's a comment and a question, and it says, apparently light use vehicles is not a significant source of ground level ozone pollution. Since this is a secondary pollutant and we know that it is formed from different chemicals in the air, would it be suggested to look into other anthropogenic sources like outputs from at-home activities? And that could be something related to also the pandemic. Would someone like to take on this one? I think I'll open up to everyone.
I typed a quick answer into the message there, but I'll just repeat it verbally. I think how I would frame it is that light duty vehicles aren't a dominant source of ozone pollution in California at the present time. They were dominant in 1960 and 1970, but the control programs that we've implemented in the decades since have been very effective. And so at this point, we've drawn down that source, and now we've got a mix of lots of different sources that are contributing. Now, light duty vehicles are still a part of that. And so I don't think they get a pass moving into the future. They have to be part of the overall solution, but we're going to have to address sources from across our entire economy, things that are both in our homes and in our warehouses and in our factories, like everywhere is going to have to be part of where we're going. And so light duty vehicles don't get a pass, but I don't think that they're the number one dominant source anymore, is how I would state it.
Yeah, I think that's a great point. And I just like to say that we do I mean, it's not exactly obvious, but we do regulate some home sources, right? Like your hot water heater, has to meet a certain NOx standard, right? And there's the paint that you use, to paint your bedroom needs to meet some standard. So we do already regulate those, but there's another big source of ozone forming pollution are lawn and garden equipment, right? And that's something you use at home. So there's some efforts at the state level looking more into that. And then, we have some efforts to incentivize electrification of that equipment. So, there is a push at the household level as well.
Great. So we got a question, and I'll just go ahead and read it. I presumed that disadvantaged communities would be unable to telework and therefore would continue to be traffic contributors. Trucks also must continue to move goods and are the biggest polluters, I guess, in this case. My question is what is the most compelling information planners should use when addressing the needs for VMT reduction? What online sources should we be using to gather and communicate needs and alternatives captured in this webinar? For example, I think a good one is Scott with the work with the warehousing rulemaking. And it's more of a comment that the presentation is highly technical, but still needs to be summarized in a way that communities and regions can understand and invest appropriately in infrastructure that shifts modes out of autos and also shifts towards more light duty. I'll open that up to everyone again and see if anyone has any thoughts. I think Shams might have something to say first.
Yeah, I mean, especially with some of the new regulations coming with like SB 743 that Caltrans have, we have this increased impetus to reduce VMT in general. And the planners who actually do the long-term forecast, we know that how difficult it is to have projects that can actually do that. We still at one point need to spend the infrastructure dollars, but at the same time reduce VMT. It's a tough job. And there is always that kind of the cognitive dissonance, I think, is between the planners and the agencies that are usually just building more stuff. How do we kind of balance it? That being said, the levers or the policies for reduction of VMT is well known. We know that we need to do more adoption of transit. We need to do more adoption of active transportation modes. We need to do like transit-oriented development, change the land use pattern. So even though these are known, these are hard to do. And I think COVID, what it has shown us is that how difficult it is to maintain, not only to maintain the balance, even if we achieve that VMT reduction, the means that we use to reduce VMT. So let's say telecommuting or some sort of changes in warehousing activity, that itself might cause imbalance in the different communities. So we need to be cognizant of whenever we are crafting policy regarding VMT reduction, we need to think about how that would impact the different communities differently. And that being said, what I would like to say, the planners specifically who are doing the long range transportation planning, what we can do is that we need to think about some alternative metrics, specifically regarding to, like I know some of the projects that might not show significant potential of VMT reduction in the long-term planning model, but still we need to ask ourselves those critical questions like whether or not we are doing the right stuff, because some of the changes because of this policy implementation would be behavioral and social. And not a lot of them are actually our models, our activity-based, even our state-of-the-art activity-based model are not capable of capturing these behavioral trends. So I would say for planners, it's critical that we use not only the numbers that we see on the screen, but also the judgment that we have regarding people's behavior and probable choices.
Then maybe I can just make a quick comment from an air quality perspective. So yeah, we also care about VMT, but we really care more about the emissions that comes from that VMT. And one way that we aim to address this is with near zero and zero emission trucks, right? So our technology advancement office works really hard to push along that technology, truck electrification or natural gas or hydrogen vehicles, not only trucks, but also off-road vehicles, right? Construction equipment. So that's where you still can move goods, but the emissions are much lower.
Yeah, and adding to that, one of the things, in addition to shifting towards the zero-emission vehicles, is really making sure that the most recent and most up-to-date understanding of additional air pollution coming from non-tailpipe emissions are well characterized in future development strategies. So things like brake wear and tire wear, for instance, are, I wouldn't call it an emerging research topic, but they are topics that have been researched in more recent years. And these are something that is very highly variable, just like what Sham said, depending on location, depending on the activities that the road had historically. For instance, changes the composition of road dust and the type of residual products that are on the roadways. And so these will continue to be a source of pollution, directly emitted pollution or fugitive pollution. And so, as for planners, the important point here is to not just look at directly emitted tailpipe emissions, but also those air pollution that are associated with sources that are being controlled.
Great, thank you so much for that, for those answers. I think that really helped. We also got a question related to about logistics expansion. Knowing what we know about fuel economy, what are your projections regarding putting more vehicles on the road in response to logistics expansion? More vehicles equals slower travel, equals more emissions. And so I think is perhaps your thoughts on the impacts of logistics expansion, perhaps how to, kind of turn it around in some way. And maybe Shams and Scott, we might want to start with this, and anyone else want to jump in?
That's a tough one. I think I'm going to defer to Shams. I'm going to pass. It's a great question.
Yeah, at least for now, in the logistics side, the two emerging trends that we're seeing is that more online shopping and e-commerce activities, and at the same time, the corresponding warehouse development that's happening around that. And so it's hard to understand whether or not there will be more vehicles because of that, because this is still an evolving science, the supply chain around logistic operation. As Scott has mentioned, like this, I haven't read that rule 2305, but I'm very interested in that. How do we make sure that we still get, because I think the Amazons are going to be there, the eBays are going to be there, people's behavior are going to shift, but how do we make sure the logistic operation does not add more vehicles on the road? And if it adds, then if it adds like more energy efficient types. So I think these are two separate questions, and that's how we can try to target them. And actually now is the time. CARB and AQMD, all of us, we can work together to make sure we tackle each one of those questions separately, and hopefully that would lead to less emissions and less air quality problems.
Yeah, I think also I'd be really interested. I don't know kind of the state of the science with this, but I mean, I know from my personal experiences, during the the heart of the pandemic, we didn't shop in stores, so I ordered a lot more stuff online that came to my house, but I also wasn't contributing my own VMT by driving out to the store. So, I kind of wonder the balance between them.
Yeah, trying to get that right balance is, I think, a really important question. And I know there's work throughout UCITS being done on some of the more on the behavioral side from a consumer standpoint, and how to hopefully nudge behavior in a more sustainable way, but also work being done on the fight at the curb, for example, and what it matters to, for example, double parking and congestion that can result from logistics vehicles. So I think that's still a very open research topic, and something that has important implications when it comes to air quality, and something that actually came very much out of the COVID-19 pandemic. This has been going on, we've been shifting to e-commerce for some time, but this really accelerated that shift. So,
so
go ahead.
Stephen, sorry, before we move along, I think there is a common understanding in some of us that more congestion leads to more emissions. But we need to think about the long-term consequences. Sometimes, specifically, the proponents of highway development have been saying this for a long time, but we know that sometimes freeing up congestion by adding more lanes might lead to induced traffic, and that in turn might increase the emissions overall. So we need to be thinking about, when you craft policy, specifically transportation policies, what are kind of the 10-year view, 20-year view, and things like that.
Yeah, that's a fantastic point about the induced demand. Thank you for that. So we're about running out of time. So I'm actually going to wrap this up with this. Thank you so much all for being here for this webinar, for providing your expert thoughts, the fantastic research from UCITS, and then also the wonderful guest responses. So a few things before we wrap up. First, if you would like to contact the presenters and the respondents, we recommend that you reach out to them directly. I think their emails should be posted in the chat, but it'll definitely be available through the website. And so you can also go back to the recordings as well as the presentations for this. Those will all be uploaded in the upcoming few days. There's a couple other things before wrapping up. First, there'll be a webinar featuring UCITS funded research on the effect of COVID-19 on long-term travel behavior on June 17th, again from 12 to 1:15. Information for registering for the webinar is available in the chat. Second, this webinar qualifies for 1 AICP CM credit or 1 professional development hour credit. Information for obtaining the credit is located in the Zoom registration confirmation email for the webinar. If you have any questions about the webinar or anything else you would like to know about UCITS, please feel free to reach out to me at steven.wong@berkeley.edu. Thank you again to all of our presenters and guest respondents today. Have a wonderful day, and we hope you stay safe during this time.